So in this chapter, we're going to talk about extrasolar planets, which are planets that orbit other stars. But all the ones we're going to be talking about are ones that we have found in our galaxy. There's four main ways that we detect extrasolar planets, and we're going to go through all four. First one, direct detection, means you actually take a picture of the planet. So let me show you some of the best examples we have. So it's really difficult to take a picture of a planet because it's going to be so close to the bright star, and usually the camera will just be saturated by the star and we won't even see the planet. So here is a star, and this would be the planet. That's an actual photo. In this case, the star would have been too bright and we never would have been able to see the planets. So we played with the image a little bit. You have to have light coming from two different telescopes or two different sources, and you put them together and you interfere the light waves. Right? So light waves can constructively interfere and the waves can get bigger, or light waves can destructively interfere just based on their timing. So if you interfere the light just right, you can cancel out the starlight. That allows you to take a picture of the fainter planets. But when you use interferometry to cancel out the starlight, you get this ripple effect around the star. So that ripple effect is not real. Beta Pictoris b, the sun was down in here. It was too bright, so we used interferometry to cancel it out. That's why you have these ripples. There is a planet here. And I probably should have showed you this picture when we were talking about the formation of the solar system, but this is a very new image of a system called HL Tau, and it's a real picture of a forming solar system in our galaxy. And you can actually see the places where the forming planets are clearing out their orbits. So this is an amazing picture. This is the last example I'll give you of direct detection. The star was down here. We used interferometry, so that gives you a lot of artifacts along this picture, a lot of speckles. And here's the planet. In this case, it is impressive that the planet is so far away from the star, because this ring right here is the location of Neptune's orbit. The second way you can detect a planet is by watching the gravitational effect of the planet on the star. So we're going to call this indirect detection. You do not watch the planet, you watch the star. Okay. So as the planet goes around, it tugs on the star. Our planets do this to our sun as well. Jupiter is the most massive planet, and Jupiter is pretty far away from the sun, so the effect is much weaker in our solar system. Nonetheless, finding this is still pretty tricky. You have to be able to measure the positions of stars very, very accurately. So a star with no planets might have traveled on a straight line through our sky as it's orbiting around the galaxy, but a star with planets around it would oscillate around that. If this effect is too weak, we can use one of the other two effects. So again, this is going to be indirect. So you're not watching the spectra of the planet. You're going to watch the spectra of a star. And the star has an absorption spectra, and if it's moving away from you, the spectral lines will be redshifted, and if the star moves towards Earth, the spectral lines of that star will be blue shifted. And you can plot out the amount of redshift and blue shift on a graph, right, and determine that there's a planet orbiting it. If the planet is in a really close orbit, it's easier to detect. The effect is faster. And we ended up nicknaming these hot Jupiters, and they were surprising. We didn't expect them at all. We thought Jupiters were supposed to form far away from their sun. We did not expect to find Jupiters inside these stars' frost lines. If the planet is really massive, it is a very strong effect and easy to detect. Low-mass planets are harder to find, and especially hard to find are low-mass planets in large orbits because there's hardly any effect at all. Right. When you use this Doppler method, You can determine the mass of the planet based on the amount of Doppler effect, but you can also determine the orbital radius based on how long it takes to orbit. Right? What you can't determine is the density of the planet. You can't determine if the planet has an atmosphere. Right? You can't determine a lot of stuff. You can just do size and distance. The last method that we use for detecting planets is called the transit method. Again, this is indirect. You're watching the star, not the planet. Okay. And so the transit is when the planet passes in front of the star, and that's going to dim the star a little bit. It's going to block some of the starlight. So what you do is night after night after night, you watch as many stars as you can, and you're always measuring their brightness. And then at some point, one of the stars might get dimmer for a few hours, and then get brighter again, and stay bright. And if you see 3 or 4 of these dips in brightness at regular intervals, you have discovered a planet orbiting the star. Now, you can't do this for any system. In order for you to see the planet transit in front of the star, you can't look at it as a face-on orbit. You have to find only systems that have edge-on orbits compared to Earth's point of view. So we've launched the Kepler telescope to just watch as many stars as it can automatically, and we've discovered a lot of planets this way. Okay. So this method is the only one so far that's really discovered Earth-sized planets. With this technique, you can determine how long it takes the planet to go around once, just by watching how frequently the dips happen. And you can determine the size of the planet based on how much light is dimmed. Right? A bigger planet will block more light. And there's one more thing that's really awesome about this method. Okay. You take a spectra of the entire system while the planet here is in position 1, and you're really just going to get a spectra of the star. And then you take a spectra of the entire system when the planet's at position 2 or position 3. And if the planet has an atmosphere, the spectra will change a little bit, because some of the sunlight will shine through the edge of that atmosphere and take out a couple more absorption lines. So in this method, we might be able to detect an atmosphere, and not only that, but tell you the composition of the atmosphere. So here's an animation showing the number of planets discovered each year around other stars. The blue bars represent planets discovered with the Doppler method. The pink bars are planets discovered with the transit method, and the yellow bar is brand new planets that have been announced using the transit method as well. So I went on to the online planet database a few weeks ago, and I checked out how many entries there are, and there are almost 5,500 planets listed in that database. Right. Truly confirmed planets with really good data behind them, 1,600. That's still really impressive. So this chart is in your book. It's a little bit too in-depth for me to lecture on without it getting really boring. So I would say go through this and try to just think about it, reason it out, why it makes sense that if you can see the planet, you can get a spectra of it. Why, if you're using the transit method, you can detect small planets. Okay. So take some time and go through here.